Okay, so in this video I will quickly comment on the solution of part 4 of question 64. The question goes like this. It says, consider the following set, which is a very complex set, one of the hardest you see in this topic, and establish whether this set is path connected or not. Okay, I claim that this set is not path connected, and I'll show you the argument, which is extremely non-trivial argument, but something which we need to at least know. So I will show it is not path connected by doing this, by just choosing 2 points which are in this set. That's my choosing. x0 is 0, 0, and x1 is 1 pi and 0. This is a point which satisfies this criteria, and this is a point which satisfies these criteria. So both of these points are in my set. Okay, that's what I say here. Both of these points are in my set. And I will show you that these 2 points, you will never be able to connect them by continuous path. I will show you this by contradiction. So let's just assume we do have a path. We do have a continuous path. That's a 0, 1 to my set S, and such that this path connects my points x0 and x1. Okay. I will construct very special points, x dash sub k, like this. Actually very special sequences, and x double dash sub k, like this. The reason or motivation for these sequences is that these are the sequence where sign is 0, and this is the sequence where sign is 1. I will also assume that my function, my path, has the following components, x and y. Each of them are continuous functions. X of t is a continuous function, y of t is a continuous function. And they also satisfy the following relation if x is positive, right? Because my path is declared to be within my set, and when x component is positive, it means that my path must satisfy this relation. So the key observation, the key line in the whole solution is coming right now. So first we observe that my sequence is within this interval 0, 1, and pi. It's just comes right from the definition of those 2 sequences. Second, I will observe that this x of t is a continuous function, right? And this continuous function, it has the following property. It is defined on this interval 0, 1, and at the left point on of this interval, it is 0, first component of x0, and at the right point of this interval, it is first component of x1. So my function xt at the endpoints of 0, 1, it takes these 2 values, 0, 1, pi. So by IVT, by the intermediate value theorem, there are points within 0, 1 where each of these sequences are the values of my x function. This is the by IVT. By IVT, I can have this sequence of t's within 0, 1, which deliver a sequence of x dash and x double dash when these t's are plugged into my x function. That's the IVT contribution. The other contribution we need is the Bolzano-Weierstrass theorem. This is one of those big results which mentioned in your first year math, but probably you haven't seen usage of that result much. And this is one of those examples where this result is actually extremely needed. Because by Bolzano-Weierstrass, I can take this sequence and assume that this sequence actually converge to something. I don't care where this converges go to. I just denoted this limit point by t0. But the effect which is needed, that they are converging sequences. Now the final line of the argument, it will sound like this. Now I take these sequences, t dash, t double dash, and I put this into my vector function, my path, which connects these 2 points. Look what I will have then. At t dash sequence, my vector function will be 0 x dash k. Because at t dash x is x dash k, and y at the same point supposed to satisfy this relation, and this is a sequence where sign is 0, hence we have 0 here. For the same reason, my vector function on t double dash, it's x double dash and 1 in here. Again, because this sequence was initially chosen such that sine function has values 1. And that gives me a big problem, because if I try to measure the distance or norm of the difference between these two values of my vector function, it will be, well, if you do Euclidean distance, there will be a difference of the first components in square, difference of the second components in square, and then square root. I don't care what the difference of the first component is, just the difference of the second components will give me at least 1, and that's exactly what's said here, at least 1. And this is despite the fact that these sequences, they converge to the same point. That's exactly how we disprove existence of a limit. You see, I found two sequences which converge to some point, but my function at those sequences, they may converge, they may not converge, that the distance between them stays always bigger than 1. So even if they converge, they will definitely converge to different values. So my final conclusion is these two lines, the way we construct these two lines and what they say, conclude one fact: this limit does not exist, and that contradicts to the initial assumption that the R is a continuous function. And that's how we finish the argument, and that's why it is absolutely impossible to connect these 2 points by continuous path. Thank you very much, I'm done.